Day 100 Notes, Advanced Algebra 2. Today we're going to work on interpreting graphs and real-world applications of functions. And so to start off today, I'd like to look at this particular example. We have an astronaut that weighs 130 pounds on Earth, and her weight when she's h miles above the Earth is given by this function here. Not sure exactly where the function came from, but I'm sure it was established by the folks at NASA that have done some extensive research on the matter. Now, the question becomes, what does her weight appear to be when she's 160 miles above the Earth? And what is her weight when she's 560 miles above the Earth? Now, if you're given the equation, it's very easy to calculate this result if you have a calculator in front of you. For example, if I wanted to find her weight when she's 160 miles above the Earth, I would simply write the function notation f of 160 equals 130 times 3,960 divided by 3,960 plus 160 and square that result. And we can achieve or obtain an answer from our calculator that way. Now, if we don't have a calculator in front of us, or if we're provided with a graph, just like we see here, we can interpret that solution just by looking at the graph. Now, in order to do that, we need to find the function value when x is 160. That's what this function notation is telling us. Find the function value when x is 160. Now, this graph was generated using our TI calculators, and one thing to make note of here, when you see a graph like this, they give us a couple pieces of information. This first number at the beginning, close to the origin of the graph, indicates the scale to which each tick mark represents. So I've turned on the axes here to show these grid lines, and I can show you how to do that tomorrow in class if you'd like to see. But it's also important to recognize that each tick mark here represents 20 units. Now our x value is the height above the Earth's surface, so we're now talking about height in miles. 20 miles, 40, 60, 80, and 100. 120, 140, 160. So this is where our height comes into play, 160 miles above the Earth, and the weight is shown here along the y-axis. 10 pounds, 20, 30, 40, 50 pounds, 60, 70, 80, 90, 100, and so on. So you can see when she is 0 miles above the Earth, she weighs 130 pounds. That's where the graph points to. Let's see where the function points to when she is 160 miles above the Earth. Right here. So this value appears to be her weight when she is 160 miles above the Earth. Now she is 100. Here is her weight, 100 pounds, 110, and now 120 pounds. So when she's 160 miles above the Earth, it appears that she only weighs 120 pounds, according to the graph. For 560 miles, we can do the same thing. Let's check out where she's at 560 miles above the Earth. So here's 500, 520, 540, 560. And if I draw an arrow up to this point, that represents her height. And if I follow this line all the way back to the y-axis, it looks like she weighs 100 pounds when she is 560 miles above the Earth. So we found our two solutions by looking at the graph, and we didn't have to rely on the calculations whatsoever, but we can write our results in function notation if we've been asked to do so. For our first answer, f of 160 would equal 120 pounds. So again, the function evaluated 160 miles above Earth, she weighs 120 pounds. For the second result, f of 560, the function evaluated at 560 miles above the Earth, means that she would weigh 100 pounds. And that's a good way to use a graph to interpret a solution to a real-world problem. Okay, and in this second example for today, we're discussing what's called Torricelli's law. A tank of water holds 50 gallons, and it drains from a leak that's at the bottom of the tank, which causes the tank to empty in a total of 20 minutes. So we start with 50 gallons and it empties in 20 minutes. Now, Torricelli's law says that the tank will drain faster when it's nearly full because the pressure on the leak is greater. And the volume of water, according to Torricelli's law, is given to us by the following equation here, as long as t is between 0 and 20. This is our domain restriction. We're only allowed using values between 0 and 20 for this particular calculation. Now, in this little picture here, you might be able to understand why Torricelli's law works the way it does. You imagine you've got a tank of water that's completely full. The entire weight of that water is now pushing on this point where it's leaking at the start when this thing starts to drain. But as time passes, there's much less water, much less weight pushing down on the leak. So therefore, the rate or how much this water is leaking at a given amount of time is much less as we travel forward in time. So our first objective here is to answer part A, find v of 0 and v of 20. Now, without even looking at a graph, you should be able to interpret these answers based on the clues given to us in the word problem. Find v of 0 and v of 20. Well, v of 0, that's the volume of water at time 0. How much did we start with from the beginning? We know that that answer is 50 gallons. And V of 20, we know that this tank is empty in 20 minutes, so V of 20 should be equal to 0. Those two answers, again, you should know by looking through the word problem, but if you're not sure, you can always review the graph, and we can see the solution to those questions by looking at the graph here. V of 0 means the function value when x is equal to 0. And if we follow up from that point, we see that our function result is 50. This is our indicator that the function is equal to 50 right at this top line. When t is equal to 20, v of 20 is this value here at the far end of the graph, and you can see that the value of the function at that graph approaches and eventually equals 0 at the very end. So part A is now finished. Part B, what do your answers in Part A represent? Well, clearly they mean the amount of water that was in the tank at the beginning, when 0 minutes have passed, and then the amount of water that's left at the end after 20 minutes have passed. So written out, we might say something like this. For part B, we would answer V of 0 shows the amount of water in the tank at the beginning of the leak, so when it first starts to leak, and V of 20 shows the amount of water after 20 minutes have passed. For part C, we need to make a table of values. Make a table of values of the function v of t for t equals 0, 5, 10, 15, and 20. So it looks like we have a leak in the tank and we're coming back to check it every 5 minutes to see how much water is left. Let's go ahead and make a table down below that does show that result. So if it were me building this table, I would start with t and v of t. And I like to orient my tables vertically, so we'll do that this way. Time 0, 5, 10, 15, and 20. And we'll separate those with a couple lines here. Now we'll go to the graph to find out what our results indeed are. Now I know when t is 0, the volume is 50 gallons. Let's go ahead and label these. So 0 seconds, and then after 20 seconds, we have 0 gallons of water. Let's find out what happens after 5 seconds, 10 seconds, and 15 seconds. Again, with this graph, The number in the lower corner here represents the key, if you will, the value for each of these hash marks or tick marks. So the x-axis increases by 1 unit, the y-axis increases by 2 units each. So we have 1, 2, 3, 4, here's 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and then we end at 20. Along our y-axis, we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, and 42, 44, 46, 48, and 50 at the top line. So with those those hash marks laid out here, we should be able to answer this question a little bit more clearly. After 5 minutes, our graph travels up to this point and it runs across the page to this location. We have a value at this point of 5 and let's see, 10, 20, 30. Take 2 off of 30. This is 28. After 5 minutes, we have reduced to 28 gallons. I'm sorry, not minutes, but seconds, I believe. Nope, we were right in the first place. This is actually a measure of minutes, not seconds. So we better fix that now before we go too far. 0 minutes, 10 minutes, 15, and 20. So after 5 minutes, we've reduced to 20 gallons. Let's see what we have left after 10 minutes. Now, this point is just above this hash mark here, so we're going to look straight across. This is about equal to 12, maybe a little bit higher than that, so we'll call this one 13 gallons. So after 10 minutes, we have 13 gallons that are left. So 10 minutes is 13 gallons. And then lastly, after 15 minutes, we're at this point here. Again, right in the middle between these two. And that's about 3 gallons. So after 15 minutes, we're down to about 3 gallons of water. And I think that pretty well satisfies this question here. Make a table of values for v of t when t equals 0, 5, 10, 15, and 20. So again, a couple examples here looking at graphs and using those graphs to find solutions. Feel free to use a calculator to check your work. If you wanted to find out the exact value after 5 minutes, we can change this x to a 5 and see if our function equals 28. If we wanted to, we can see after 10 minutes, we can evaluate this function and see if that's equal to 13. And lastly, we can change this x to a 15 to see if our answer comes out to be a 3. I'll leave that up to you if you're curious enough to find that solution. Otherwise, we'll leave these as it is. Tomorrow's activity in class has us dealing with looking at graphs and finding solutions for them as well. We're given complicated equations and functions to work with, to which you can always calculate a response or an answer. But again, we're working on interpreting graphs for these 2 days in class, so I want to make sure that you are comfortable and familiar with that technique. Please let me know if you have any questions. I'll be happy to help you when we're in class tomorrow.